Okay, so first of all, I must have bumped my head yesterday before class or something because I don't know what I was.
And what were you doing?
Remember this one? This one was bizarre. I don't know what I was thinking. So obviously, I was thinking infinity. When you're approaching, yeah, we're going to get an infinite answer on this, but we're not approaching infinity, right? And so we can't apply the rules of rational functions here. Now, if we were approaching infinity, this would be pretty easy. Then we would just look at the ratios of the leading coefficients, right? Does that make sense? But we're not. So we have to actually, like we did yesterday, we have to go through and figure out, we know we're getting a 0 on the bottom, which means that we're actually getting 0 over 0 on this one, right? So this is one where we had to factor it and cancel, right? If you didn't factor it, remember you had an alternate way of doing this. Because the bottom is very conveniently linear with an easy 0, this is a prime candidate for just doing synthetic division, right? Okay, so we left off, I think, where? Did we get this one squared away?
Yeah.
Are we okay on that one?
Yeah.
Wait, so
Okay.
the answer is 8 over 5.
Right. So let's wrap this one up maybe then.
I know, yeah, we did. I was just a little over.
We're all good?
Yeah.
Okay, so if we break this into pieces, we just get the limit, we'll take the 8x over the 5x times the limit of sine 8x over 8x times the limit of 5x, over sine 5x. But one thing we got to do here, we got to be careful. Here we can just let x go to 0, right? Doesn't matter. We're just going to get 8/5. Here, what does x need to be approaching? This middle one, 8x, right? So we match that pattern. And here it's got to be approaching, do that again. Not x is approaching. What is approaching 0? Let me rephrase that. There you go. 8x is approaching 0. And here, what is approaching 0? 5x, right? Because it's got to match the thetas that show up in here. Okay, we good? All right. Okay, next one. Yes or no? Thumbs up, thumbs down. You want to do this one or not?
Yes.
Yes.
Oh,
Okay.
yeah.
Okay, so here's one. This is one where we've got a indeterminate form, and it's complex fractions. We'd want to first just try it. If I plug in x equals 0, though, everybody agree we're going to get 0 over 0, right? Okay, so this amounts to just simplifying. Remember, the method of complex fractions just means we're going to simplify the top, simplify the bottom, flip and multiply, and then that should allow us to cancel. It always will. And you guys get that, right? You know that if this is indeterminate, you're always going to be able to cancel stuff that removes the indeterminacy. It's you just got to get there. But you can go into it with confidence knowing it needs to work. So if it's not working, maybe you did something wrong. So on the top, what are we going to get? If I get a common denominator, what's that going to look like? What's my common denominator going to be on the top? Good. So what do I have to multiply here, top and bottom, to get that? There you go. So I got 14 of my numerator there, and over here I've got good, all divided by x as x approaches 0. So on the top, we're going to end up with the common denominator 14 over x plus 14. And if I simplify the numerator, what is 14 minus the quantity x plus 14?
Negative x.
Negative x, right? And then dividing by x is the same as multiplying by 1 over x. Okay, we good so far? Okay, and then what cancels? and that removes the indeterminacy. At that point, we could just take the limit. So I get -1/14 times x plus 14 as x goes to 0. Well, let it go to 0. And then I just get -1/14 times 14, so -1/, what is that, 196? Because when I divide by, I'm going to multiply by the reciprocal at the bottom.
Oh, so
Right.
negative equals.
Right. So this stuff right here, the numerator, just turned into that,
Okay.
right? And we just divided by, or dividing by x is multiplying by 1/x. Okay? Questions? Good? Okay, let's look at some of these then. So we want to take these limits or state that they don't exist, right? So how are we going to do the limit of g of x as x approaches -3 from the left? Yeah, which part of that, which piece of the function are we evaluating there? First one. So what is the answer to that first one? 0. This is a constant, right? So the limit of this part of the function is always just 0. The limit of 0 as x approaches anything, who cares, is 0. Okay, what about part B? The limit of g of x as x approaches -3 from the right. So which part of the function are we on? Second one, right? So we're inching back towards -3 from values bigger than -3, right? So if I evaluate that directly, as x approaches -3, what do I get? What do I get? 0, right? -3 squared is 9. 9 minus 9 is 0. Square root of 0 is 0. Okay? What about the limit of g of x as x approaches -3? 0. How come? Say it again. It's the right. Okay, so but we're not actually evaluating the function. We're evaluating the limit. My question, the answer is 0, but I want to know why. Good. And make sure you understand this. It's not because this one is true. The answer is 0, but not because g of 0 equals 0. That's completely irrelevant. That doesn't matter, right? Remember, the two-sided limit only exists if the one-sided limits exist and agree, right? We could do something crazy, like we could even define, let me make a point here, we could define a third part of this and say g of x is equal to 10. Let's say we just make this x is less than -3, and it's equal to 10 when x equals 3. In which case, g of 0 would actually equal 10, but the limit would still equal, everybody get this? What would the limit equal? If I defined a fourth part of this, which was, so I'm trading this in for just x is less than -3. And I'm saying we're going to extend this function so g of x equals 10 when x actually equals 3. Did that change the answer to part A? It didn't. You're right. It didn't because, remember, the limit doesn't care at all about what happens when you actually get there. It just cares about what's happening as you approach that value, right? So we would still be, as x approaches -3 from the left, we would still be on that part of the function, right? See my point? As we approach 3 from the right, we would still be on this part of the function. And the limit from the left and the right would agree, right? That makes sense in the context of a graph, too. Like, we looked at a lot of graphs like this, where if we had something, I'll draw you a picture. Like, let's say we're approaching +3 this time. If I have some function that's doing this from the left, and it's doing this from the right, and the actual value of the function at 3 is right there, where does the ant think he's approaching from the left and the right? Same place, right there. it's irrelevant that that's not actually where you would be though. Okay, it's an important point. Give me a thumbs up on that, or thumbs down, or, okay? All right. The limit of g of x as x approaches 3 from the left. What's that going to be? So which part of the function are we on? If we're approaching positive 3 from the left, middle one. Okay, and so we're going to get 0 again, aren't we? Right, if we evaluate that directly, we get 0. The limit of g of x as x approaches positive 3 from the right, that would put us down here. What would we get? 6. So the limit of g of x as x approaches 3, right? Doesn't exist. Okay? All right, so evaluate the limit of f of x as x approaches infinity and as x approaches negative infinity. This is a quick one. What's the answer? Oops. Limit, we can combine these. The limit of f of x as x approaches plus or minus infinity is what? 0. Right? So what's the horizontal asymptote then? How would we write that as a horizontal asymptote? Y equals 0. Okay. Make sense? Okay. How about down here? Evaluate the limit of f of x as x approaches infinity and negative infinity. If this is f of x, well, the limit of f of x as x approaches plus or minus infinity is what? 1/5. What's our rule? Yeah, if we're taking a limit at infinity, we just look at the ratio of the leading terms, right? If we have the same powers of x in both, right? And really, that's what we did up here too. But this time, the limit of the ratio of the leading terms, the bottom was more powerful than the top, so it went to 0. Here, it goes to 3/5, which is, or 3/15, which is 1/5. And so obviously, what's the horizontal asymptote then? Okay? Bottom one. So what about this time? Okay, once again, we're just going to look, if we've got rational functions, we're just going to look at the ratios of the leading coefficients. Those are the dominant terms for large values of x. All right? So at infinity or negative infinity. This time, what happens? If I simplify that, so that's equal to, so the limit of f of x equals the limit of 42x to the 6th over 17x to the 5th, and we'll do plus or minus infinity, although we might get different answers to that, right? So what does that simplify to? I don't think 42 over 17 doesn't reduce, but x to the 6th over x to the 5th does. What do we get? What do we get? What's x to the 6th divided by x to the 5th? X. So if x approaches positive infinity, then what are we going to get? Well, we're going to get we get that x is on the top because 6 is bigger than 5, right? Okay, you're right. You would have a slight asymptote. This isn't asking for that, though. This is only asking for horizontal asymptotes. So on the test, so I'm not going to ask you to actually do, later on in the year, we'll do that on tests. When we get to like using functional analysis, when we plug in all our knowledge of derivatives, then we'll come back and do a much more exhaustive analysis of what a function looks like. And we'll throw in slant asymptotes. For now, we don't really, I mean, we can do it, but it doesn't really help us very much. Okay, so we won't do that on the test. I know I gave you a couple on homeworks to do, which is good. We'll come back to it. But I'm not going to test you. Okay? So you're right, it is a slant asymptote, but all we want to know here is what's going on. What's the limit let's do this first of all, as x approaches positive infinity. Infinity, for sure, right? Because that's going to infinity. I get a positive coefficient times a positive infinity. It's positive infinity, right? Okay. The limit of 42 over 17x as x approaches negative infinity is going to give me a positive coefficient times negative infinity is negative infinity, right? Which fits with a slant asymptote, doesn't it? It's going to go like that, right? Did we have to do all that simplification? No, we didn't. We really didn't, right? We could just use our rule. We know here that because the top is a bigger power than the bottom, that automatically tells us that at infinities, right? If we go left or right forever, we know that our answer is going to be infinity. It's just a matter of what's going to be the ratio of the signs. Does that make sense? So we didn't really have to do any of this stuff. I did it to make a point. But we could just as easily, have done this, right? The limit of f of x as x approaches positive infinity is, well, we know it's infinity because the top is bigger power. I'm plugging a positive number in, so I'm going to get a positive term on the top, positive term on the bottom, positive over positive is positive. The limit of f of x as x approaches negative infinity, we know we're getting infinity because the top, once again, is bigger. But if I'm plugging a negative value in for x, I'm getting positive over negative, agreed? Which is negative. Okay? So you could do all the analysis there without really having to simplify anything. Okay, questions? Okay. From what value of a is the following function continuous at every x? So for it to be continuous, let's first of all break this down to the concept. What has to happen for the function to be continuous? Okay, what has to be the same at both sides? The one-sided limit, so we have to have a limit, don't we, right? The limit has to exist, what else has to be true?
The limit of f of x has to be below x.
Okay, so function has to be defined there, right? That's kind of criterion number one, right? And this was, I want you guys to make sure we're getting on. So first criterion is function exists. Second criterion is limit exists, meaning both sides join, right? Have to approach the same value. And then in order for it to be continuous, the function has to equal the limit at x, right? If it didn't, we could end up with something like, like this. Right? Where function exists, limit exists, but they're not equal. Right? So what would we have to do here? Well, the function exists. The function has a value of what? F of 9 equals what? 9a, yep. Okay, what's the limit of f of x as x approaches 9 from the left equal to? 9 squared minus 27. So what's that give us? So 54? Okay, what's the limit? Boy, how'd that happen? Limit of f of x as x approaches 9 from the right. 9a, good. Okay, so it's equal to the value of the function there, which we could see. What do I have to do then for this to be continuous? What has to be true? Yeah, those have to be equal, don't they? Limit from the left has to equal the limit from the right. And so that's, with 9a equals 54, what's a? Okay. Right? Okay, how about this? Find the point of discontinuity, first of all. Okay, well, where would that have to be? At 1. Okay. So let's see, is this removable or non-removable? Let's see what's going on here. The function is equal to 1 minus x squared for all x not equal to 1, and at 1 it equals 4. What's the limit of f of x as x approaches 1? Two-sided limit, what's that equal to as x approaches 1? Zero, right? Because as x approaches 1, we're there, aren't we? Right? As x approaches 1, I can evaluate that directly. That's easy. I just get 1 minus 1 squared, so I get 0. The value of the function at 1 is equal to 4. So this makes sense? It's removable because all we'd have to do to patch the hole is just redefine this part of the function. Instead of setting the function equal to 4 at 1, what should we set it equal to? 0. Okay? All right, so vertical asymptotes. This is a good one. This is a good one. Everyone pay close attention to this because people generally have a hard time with this. So we want to find all the places where there are vertical asymptotes. This is a tangent function. You can think of this in terms of a tangent graph if you'd like to. I never do. I mean, we know what that looks like, but I think it's easier just to break these down into sines and cosines, right? So g of theta equals sine of pi theta over 22 divided by cosine pi theta over 22. So first of all, somebody tell me, where are vertical asymptotes going to exist? I don't want specifics, but just tell me, like, how are we going to look for it? Okay, where the denominator is 0, right? So asymptotes exist where cosine of pi theta over 22 equals 0. Well, where does cosine equal 0? And this is a unit circle question, right? Where does cosine equal 0? So it's going to be, well, it's more than that. It's going to equal there and there. But there are infinite laps of the unit circle, both forward and backward, right? So it's going to be every one of those locations that ends up there and there. So how do we say that? Okay, so it's going to be, okay. Odd values of pi halves, right? So remember how we did that. How do we say odd values of pi halves? Odd values of pi halves. So I've got to somehow say an odd number times pi over 2, right? What's my way of saying an odd number? If we're going to let something like, let's just say n is an even, or is an integer, right? Any integer. Or we could say n is an element of integers, or n represents a set of all integers, right? However you want to say it, if n represents any integer, how do we limit ourselves to just the odd integers? 2n minus 1 or plus 1. Yeah, and I can't remember which one we did. I think usually we did minus. I think usually you do plus because you let n go from 0. It doesn't make any difference though. You get the same answer either way. So if those are the values where cosine theta equals 0, we're just setting those equal to pi theta over 22 and solving for theta, right? Cosine equals 0 when theta is equal to that, right? So we just solve that little equation. Pi theta over 22 equals 2n plus 1 times pi halves. So what can we do to solve this? Well, we could divide both sides by pi. We could multiply each side by 2, how about? Or actually, multiply side by 22, just get the theta by itself. So theta equals 2n plus 1 times 22 over 2, right? Which is what? 11. Which is just equal to 22n plus 11, where n is any integer. Okay? Make sense?
So that's the answer.
That's the answer, right? They want to know,
Can you go down?
oh, hang on a second, what were they asking for?
The vertical.
Okay, so it's going to be, those are going to be the values of theta. Yeah, so that's what we're looking for, right? We're just looking for the values of theta, and it's going to be theta equals in all those places. Those are the values of theta where we get vertical asymptotes. Okay. We could check it. If I plug one in, it's my original function, 22n plus 11, what are we going to get? Well, just look at the bottom. Pi times 22, would we get 22n plus 11?
Yes.
So if I plug that in for theta, I get cosine of pi times 22n plus 11, all divided by 22. Well, isn't that just pi times n plus 1/2? That's what Gabe told us, right? Isn't it? Right. Odd multiples of pi halves, right? You see that? So if n is 0, we just get pi halves. If n is 1, we get 33 over, so we get 3 halves pi, right? N is 2, we're going to get 55 over 22, so 5 halves pi. It works. Questions on that one? All right, how about this one? Use analytical methods and/or, well, no graphing utility, just analytical methods to identify the vertical asymptotes, if any, of the following function, okay? So we gotta really, there's almost no algebra, it's just thinking. What are we gonna do on this? I wanna rewrite this thing, right? First of all, what's 1 over cosecant equal to? No, just sine, right? Okay, so we could rewrite this as 7x plus 1, the quantity 7x plus 1 times sine x over cube root of x. Well, where are vertical asymptotes? Where could they exist here? I mean, what's going to happen to cause it to be a vertical asymptote? Denominator 0. Yeah. Okay, so all we got to do is ask ourselves, when does the denominator equal 0? Right? Cube root of x equals 0 when x is 0, right? That's it. Okay. Questions? Okay. Determine the intervals on which the following function is continuous. Okay, so it's continuous everywhere where it's not discontinuous, right? Where would a function be discontinuous? Now, if we have an obvious piecewise function, could be at the junction, right? But that's not a piecewise function. Where else would a function be discontinuous or undefined? Yes?
Underneath the radical.
Okay, underneath an even radical, right? Take an even root, then you can't take an even root of a negative number. Is this an even root or an odd root? Okay, well, it's tricky because we've got an even numerator and an odd denominator. So what is it? Odd or even root? It's odd, yeah, because the bottom determines what kind of radical it is, right? This is the same thing as saying this is equal to 8x plus 9. You could say it two ways. It's either the ninth root of that squared, or it's equal to the ninth root of 8x plus 9 squared, right? Either way, it's a ninth root, isn't it? Yes, sir.
So if we took just like we just took like a negative number to the two ninths power, it'd always come out even, right?
Always comes out positive. Because you're
Yeah,
squaring it, right? Because the top is even, right? So that means you're going to be taking this to an even power. So it's always going to ensure that the answer is positive. But then you're just taking a ninth root. Okay.
Okay.
Right. Make sense? This would have been a little stickier wicket here if we had had something like g of x equals 3x minus 7 to the 3/4. Right? Where would that function be continuous? Well, only where it's defined. And is that an even or an odd root? That's an even root. So now we would have to say that whatever's inside this can only be non-negative, right? So in this case, we'd have to say something like 3x minus 7 has to be greater than or equal to 0 to solve that inequality. Right? Okay? When they say determine the intervals, what kind of notation are they wanting? Interval notation, right? So if we solve this one, we would get 3x is greater than or equal to 7, so x is greater than or equal to 7/3, so it would just look like something like that, right? First one is all real numbers, so it would just look like that. Okay.
This isn't all really. This wasn't even really do something like that.
Like the bottom one.
Yeah.
Yep. Okay, what about this? Determine the intervals on which the following function is continuous. Okay, this is a pretty easy one too. It's continuous where it's not discontinuous. How are we going to know where it's discontinuous? We would factor, wouldn't we? Right, so we set this equal to x minus 1 over x minus 1 times x plus 1. Well, where is it discontinuous? -1 or 1, right? It can't be defined at any 0 of the denominator. Now, sure, what's happening at 1 is we just have a hole, right? We have a vertical asymptote at -1. One of them is removable and one's not removable, but they're still discontinuities. Right, so we have to write this one as like that, right? The interval notation.
Well, we can maybe one more. You know, I actually.
Well, because the only values, that's the same thing as saying x cannot equal plus or minus 1. But just writing it with interval notation. Okay. Yes, sir.
On the test, it asks for equation should be like that, but with x is not equal to 1, that's just.
Like this?
Yeah.
I think
Well, we have to like.
I think you got it. I think it actually it wants interval notation, so I think you got to put it in that way on this one. Okay, interpreting this graph. So let's see. Now we got this graph here. You guys can probably see that okay, I guess. So we have asymptotes where? Let's draw those in.
-1.
-1 and 2. Okay. All right, horizontal asymptote, doesn't ask about anyone. So what's the limit of f of x as x approaches -1 from the left? Infinity. The ant's walking up to infinity. As we approach -1 from the right, walking up to infinity. Approaches -1. Does that mean the limit exists? No. But we can at least say that it consistently approaches infinity from both sides, okay? As we approach 2 from the left, 2 from the right, so the limit, okay? You can't say anything about it, but the two-sided limit. Define g of 6 for the function so that it's continuous at x equals 6. What would we do? So right now, we've got this function, g of x is equal to this as long as x doesn't equal, what? 6. It can't be defined as 6. So really, all we're doing is we're going to trade this for a function that fills in the point. That's all we've done when we solve limits by doing more work, isn't it? Right? If I try to evaluate this directly, I get 0 over 0. So the limit of g of x as x approaches 6 equals, we could factor some things here, right? We could take a 3 out of the top, x squared minus 36, take a 3 out of the bottom, x minus 6, we could cancel those. Limit should be. And then, now what? Factor the top. Right? Cancel algebraically and evaluate. As x approaches 6, what do we get? So that's the value we need, isn't it? If that's the point that the ants think they're approaching, then we better put a dot there for them to step on if we want to make it continuous, right? Okay. Vertical and horizontal asymptotes. Okay, let's do horizontal. What are the dominant terms on the top and the bottom? What do you think?
Square root of x, so you look at those and asymptote 5.
Right, okay, so how come we can disregard the cosine x term?
It's also used with negative
It's bounded, right? It's trapped between -1 and 1, so it's, that's gonna be, those are the dominant terms, so this is equal to the limit of f of x as x approaches plus or minus infinity is the limit of 5 radical x over radical x. And those cancel, right? So I just get 5. Y equals 5 is our horizontal asymptote. What's the only value where this function is, we're going to get a 0 on the bottom? So that's the vertical asymptote, isn't it? 0 is an exclusive 0 of the bottom, right? Well, actually, we should check. Maybe it's not. What is, so if I try to evaluate this at 0, I get, what's cosine of 0? Oh, no, it is. Cosine of 0 is -1. There's 1, right? So I get -1 plus 0 over 0. So I get a number over 0. So that's a vertical asymptote, isn't it? Right? Okay. Questions?
So you can't take it even rid of a -1 with x.
You can't take an even, you're right.
So if x is negative, what does that mean?
Okay, so this function is only defined,
Positive.
it's only defined for positive values of x, but we still get a vertical asymptote there,
Okay.
right? Okay, good question. Everybody understand that question? Oh, and then intermediate value theorem. So all I'm going to say about this one is, there's a question on the test. If you've done the practice test, you've seen it. It's, all you'd have to do is review the one we did in the book about the guy walking up the hill and down the hill. I got a video of it, the notes are up there, right? It's not hard, but I want you to wrap your brain around intermediate value theorems. We'll come back to it again and again, right? You know what I'm talking about? Remember the guy walked up to the camp one day? Yeah. Okay. That's the one. I'll only give you one question, and it's essentially that question.
When they meet.
Yeah, you want to, okay, so remember, let's just review real quickly, what IVT is all about. So we want to use the intermediate value theorem to just to show, we don't have to find out when it is, just to show that there has to be a time when the two passed by the same point at the same time. Real quick, IVT. IVT, what's it say? There's the criteria that have to be met, right? If f of x is continuous on some closed interval from a to b, right? So there's criterion number one. And
G.
there exists a real number, I can't remember, called k, I think.
Yes.
Different books call it different things. A real number k such that k is between f of a and f of b. Doesn't matter which one's bigger and which one's smaller, right? If that's true, then what does the intermediate value theorem guarantee?
There must be a point where the value equals zero.
Yeah, there has to be at least one point on the closed interval, not where it equals zero, where the value of the function equals k, right? And this is a picture theorem. The easiest way to describe this one is just to draw a picture. So this is the picture that we drew, and it works fine. If that's A and that's B, and let's just say this is f of A, and this is f of b, and the function is continuous, so I can draw it without picking my pen off the board, then if there's a value k that's between a and f of a and f of b, guaranteed, there's got to be at least one place where the value of the function is equal to k, and we call that point c, right? At least one value c exists, so we call that like c1 in this case. That's c2, and that's c3. There happen to be three of them this time. There's got to always be at least one, right? Yes, sir.
Will they always be
Mm-mm.
odd
No, because I can pick, what if I pick, odd numbers? No, because what if it hits right on, what if it hits as a tangent, right? I mean, if I drew it right here, call that K2, then I'd only have one value of C for that one, right? Okay, but you can never have zero. Yeah, Kirk, you're part right, because that really counts as two solutions. I mean, kind of. If you look at, there's a way you could count that as two. It's a double root. Matter of semantics, but yeah. You were on something. All right, questions? Okay.